So this is the second lecture for the structure of atoms of class 11 NCERT book. So in the previous video I have discussed the Dalton's atomic theory and how it was not correct and what are the various constituents of atoms and how all of them were discovered. And after that we studied two model of atoms. The first one was by Thomson, and which actually showed that the atom was like a positively charged sphere with electrons embedded in it uniformly. And the second one was by Rutherford, which actually designed the atom in such a way that depicted the solar system, where sun is the nucleus and all the electrons around the nucleus is like the planets. So let's start by discussing the drawbacks of the Rutherford model that we studied in the last video. So Rutherford's nuclear model of an atom was like a small scale solar system where nucleus depicts the sun and the electrons depicts the planets. So when we talk about two charges, we talk about Coulomb's force, and when we talk about two masses kept near to each other, we talk about the gravitational force. So Coulomb's force is given by K Q1 Q2 upon R square, where K is the proportionality constant and Q1 and Q2 are the charges of the two entities and R is the separation between the charges. Is mathematically similar to the gravitational force, where G is the gravitational constant, M1 and M2 are the masses and R is the separation between the two masses. Now, talking about the similarity, so similarity between the solar system and the nuclear model suggests that electrons should also move around the nucleus in a well-defined orbit, because we know that planets also move around the sun in a well-defined orbit. So in that similar fashion, electrons should also move around the sun, move around the nucleus in a well-defined orbit. So even if the body is moving at constant speed, like if electron is moving at constant speed, but since it is the circular motion, which implies that it is changing its direction, and with the change in direction comes the change in acceleration. So that means even if the electrons is moving at a constant speed, it has some acceleration because of the changing direction. So since electron is under constant acceleration, so here comes into the picture the electromagnetic theory of Maxwell. So according to the electromagnetic theory of Maxwell, charged particles when accelerated should emit some electromagnetic radiation. So here also, like electron, it is a charged particle, and when it is like, since it is changing its direction, even if it is moving at constant speed, it is having some acceleration. So this means that it is emitting some electromagnetic radiation. So an electron in an orbit will emit radiation. The energy carried by radiation comes from the electronic motion. So this means that this radiation is emitted by the electronic motion. Okay, so this means that the speed of the electron is decreasing. So the orbit will thus continue to shrink with time, and according to the calculations, it will take an electron only 10 to the power of minus 8 seconds to spiral into the nucleus, and hence the atom would collapse. But atoms doesn't collapse in that way, right? So atoms are basically the stable entities. So this suggests that according to the Rutherford model, the stability of the atom cannot be explained, because according to the Rutherford model and the electromagnetic theory of Maxwell, the electron should bump into the nucleus at some point of time, like after 10 to the power of minus 8 seconds. But this is not the case. And also, this Rutherford model doesn't say anything about the distribution of electron in the atom. It just said that the electrons is around the nucleus in a well-defined orbit. It doesn't say like where exactly the electron is, where exactly at a particular time the electron is. So it doesn't say anything about the distribution of electrons in the atom. So these are the drawbacks of Rutherford model. Firstly, it could not explain the stability. Secondly, it doesn't tell anything about the distribution of electrons in the atom. So now comes into picture the Bohr's model of atom. So after the drawback of the Rutherford, now Bohr actually took that idea and also uh, by using three different developments at that time, he formulated his own model of atom. So what other development actually helped him to solve the problem, to solve the model of atom, were the dual character of the electromagnetic radiation, which means that radiation possesses both wave-like and particle-like properties. So dual nature of the radiation, it was the first development that was made in those days that helped Bohr to design his own model of atom, and the second development was the experimental results regarding atomic spectra, which can be explained only by assuming the quantized electronic energy levels in atom. So I'll just explain what this quantized energy level in atoms means. It means that the electrons are present in different orbitals per se, and these orbitals, the energy levels of these orbitals are basically, these orbitals are only called the energy levels, and the energy levels are quantized, which means that it is in the multiple of some integer. So actually these two theories helped Bohr, along with the previous two theories for the model of atom, to formulate his own Bohr's model of atom. So in the last slide we saw that Bohr's model was basically guided by the two already discovered principles, one out of which was the dual nature of the electromagnetic radiation. So we'll dig into that, what exactly is it all about. So only after we know all of these two principles, then only we can understand the Bohr's model of the atom completely. So first we will be talking about the wave nature of electromagnetic radiation. So this was first given by scientist named James Maxwell in 1870. So he suggested that when electrically charged particles moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. And these fields are transmitted in the forms of waves, which are called electromagnetic waves or electromagnetic radiation. So जेम्स मैक्सवेल ने कहा था कि जब भी कोई चार्ज पार्टिकल ऑसिलेट कर रहा होता है तो उसमें से एक इलेक्ट्रिकल एंड मैग्नेटिक फील्ड्स प्रोड्यूस होती हैं. तो ये जो इलेक्ट्रिकल एंड मैग्नेटिक फील्ड्स हैं वो वेव्स की फॉर्म में ट्रांसमिट होती हैं. तो उसने ये कहा था वेव के फॉर्म में. फिर ये जो इलेक्ट्रोमैग्नेटिक वेव जो ट्रांसमिट होते हैं इसके मोशन के बारे में विल बी टॉकिंग अबाउट. सो इलेक्ट्रोमैग्नेटिक वेव का जो मोशन होता है वो थोड़ा कॉम्प्लेक्स नेचर का होता है. इसके कुछ प्रॉपर्टीज यहाँ पर मैंने लिस्ट किए हैं. सो the oscillating electric and magnetic fields produced by the oscillating charged particles are perpendicular to each other and both are perpendicular to the direction of propagation of wave. जैसे जो एक चार्ज पार्टिकल जब ऑसिलेट कर रहा होता है तो उसमें से इलेक्ट्रोमैग्नेटिक रेडिएशंस निकलते हैं. इलेक्ट्रोमैग्नेटिक रेडिएशंस मतलब इलेक्ट्रिक फील्ड्स एंड मैग्नेटिक फील्ड्स. तो ये जो दोनों फील्ड्स होते हैं जो ट्रांसमिट हो रहे होते हैं ये दोनों फील्ड जो है एक दूसरे के परपेंडिकुलरली निकलते हैं और ये जो ओवरऑल ये दोनों फील्ड्स तो एक दूसरे के परपेंडिकुलर होते ही हैं प्लस ये direction of propagation of wave के भी perpendicular होते हैं. So there is a picture in the next slide that we will see. And also, unlike sound waves or water waves, these electromagnetic waves do not require any medium and can move in the vacuum. So you don't basically need this electromagnetic radiation does not need any medium to travel. It can travel in vacuum as well. So this is one of the property of the electromagnetic wave motion. And also there are various types of electromagnetic radiation. They differ from each other from wavelengths and frequencies. So and these constitute what is called as electromagnetic spectrum. तो हम लोग कुछ लोग जानते होंगे कि इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम क्या होती है. सो बेसिकली जो लाइट का रेंज होता है हम लोग बात करते हैं कि ऐसा लाइट जो आपको दिखता नहीं है, ऐसा लाइट जो विजिबल रीजन में है जो आपको दिख रहा है, ट्यूब लाइट्स, बल्ब्स. तो ये सब जो वेवलेंथ एमिट कर रही है ये विजिबल रीजन में वेवलेंथ एमिट हो रहा है, इसलिए हमें दिख रहा है, तो ये विजिबल रेंज में आ रहा है। बट कुछ कुछ लाइट्स ऐसे भी होते हैं जो हमें दिख नहीं पाता होता है, क्योंकि वो विजिबल रीजन के पार होता है, मतलब उसकी वेवलेंथ जो होती है या फिर विजिबल रीजन से ज़्यादा होती है या फिर विजिबल रीजन से कम हो रही होती है। जो ये पूरा ही स्पेक्ट्रम है वेवलेंथ का, बेसिकली जो पूरा ही जो है ये, मतलब डिफरेंट वेवलेंथ्स का जो एक स्पेक्ट्रम है उसको इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम कहते हैं, और ये सारा ही बेसिकली इलेक्ट्रोमैग्नेटिक रेडिएशन ही है। तो यही लिखा हुआ है कि जितना भी तरह का, जैसे कि विजिबल लाइट में जो रेडिएशन निकल रहा है वो उसका जो वेवलेंथ है वो विजिबल रीजन में है, जो यूवी लाइट निकल रहा है वो भी एक तरह का इलेक्ट्रोमैग्नेटिक रेडिएशन ही है, बट उसका जो वेवलेंथ है वो यूवी रीजन में है। तो ये सब बहुत अलग अलग तरह का इलेक्ट्रोमैग्नेटिक रेडिएशन होता है। इट इज बेस्ड अपॉन डिफरेंस इन दी वेवलेंथ। This is the pictorial representation of what I was talking in the last slide. So this is the motion of the electromagnetic radiation. So this these the lines in the blue are the magnetic field component of the electromagnetic radiation, and the red one is the electric field component of the electromagnetic radiation. And here, this is the 3D graph where x-axis is the direction of propagation, and towards the xy plane it is the magnetic field component, and towards the xz plane it is the electric field component. So this is how it's the motion of the electromagnetic radiation is similar to what exactly is represented over here. So this is the electromagnetic spectrum I was talking about. This is the whole range of the electromagnetic spectrum. So it comprises of various uh, wavelengths of frequency on whatever both the scales are written over here. So wavelength and frequency are these two parameters are inversely proportional to each other. So these long radio waves has the uh, they are lower in energy, so this means that they have high wavelengths, and these gamma rays, they are very high in energy, means they have very low wavelengths. Energy parameter is directly proportional to the frequency. We know this formula, E is equals to h mu upon lambda, where mu is the frequency and h is the constant and lambda is the wavelength. So this is visible range that is visible to us. So it is very evident that from this broad electromagnetic spectrum, only very thin layer of the spectrum, or we can say a very small range of the wavelength or the frequency, whatever unit you consider, is visible to us, the human eyes. So how do we represent this electromagnetic radiation? So in order to represent any quantity, we need some units. So here, this electromagnetic radiation can be represented by two, actually three, but first let us talk about two units. First, two basically entities. First is the frequency, that is represented by mu, and second is the wavelength, that is represented by lambda. So frequency has the SI unit of per second. So basically it is frequency is defined as number of cycles that is taking place per second, and wavelength, the SI unit of wavelength is that of the length, that is meters. And in vacuum, all these electromagnetic radiations, regardless of wavelength, travel at the same speed, and that speed is nothing but the speed of light, which is equal to 3 into 10 to the power of 8 meter per second, and is given by equation C equals to mu lambda. And also the third entity by which we represent this electromagnetic radiation apart from frequency and wavelength is the wave number, which is another entity, and this is actually nothing but the reciprocal of the wavelength. So the SI unit of wave number would be meter per second. So it is defined as the number of wavelengths per unit length. Now we have already seen about the wave nature of the electromagnetic radiation and various things regarding that. Now let us move and talk about the particle nature of the electromagnetic radiation, which is given by Planck's. So we will be studying basically the Planck's quantum theory and where this word quantum came from in the next slides. So, the experimental phenomena such as diffraction and interference can be explained by the wave nature of the electromagnetic radiation. But apart from those, there were several experiments that were not able to explain, that wasn't able to be explained by the wave nature of the electromagnetic radiation. So, for which particle nature of the electromagnetic radiation needs to be coined. A few of these are the photoelectric effect and the nature of the emission of radiation from the hot bodies and the line spectra of atoms with special reference to hydrogen. All of these will be discussed later in the slides. So let us talk about the phenomenon of the black body radiation, which was given by a very famous scientist called Max Planck. So the ideal body which emits and absorbs radiations of all the frequencies is called a black body, and the radiation emitted by such a body is called the black body radiation. So basically, we first need to understand what a black body is. So a solid, like any body which has the capacity or capability to absorb and emit radiations of all the possible frequencies of the electromagnetic spectrum is called the black body, and the radiation that is emitted by such body is called the black body radiation. So, the exact frequency distribution of the emitted radiation, that is the intensity versus frequency curve of the radiation from a black body, depends on its temperature. So, basically, it is a temperature dependent phenomenon. So that means at a particular temperature, a particular frequency will be emitted by the black body. Basically, the frequency that is emitted by the black body depends upon the temperature. As you increase the temperature of the black body, then the frequency of the emitted radiation will also increase. And also, this third point is very important. So, at a particular temperature, intensity of radiation emitted increases with the decrease of the wavelength, reaches a maximum value at a given wavelength, and then starts decreasing with further decrease of the wavelength. So, basically, this point explains an experiment. So, at a given temperature, when the intensity was studied with respect to the wavelength at the given temperature, then what was observed. So basically, when the wavelength was decreased, then the intensity of the radiation that was emitted increases, and it reaches a maximum value, and with further decrease in the wavelength, this maxima then decreases, that is the intensity further decreases with the decrease in the wavelength. So this particular experiment was not able to be explained by the wave nature of the radiation. So this particular experiment, Max Planck explained by the particle nature of the radiation, which we will be studying in the next slide. So this is the curve for the wavelength intensity relationship. Here it can be seen that for a given particular temperature, considering T2 greater than T1. So first of all, it is very evident that when the temperature will be higher, then the intensity of radiation will be higher as well. So as discussed in the last slide, I told that at a particular temperature, as the wavelength decreases, then the intensity first increases and reaches a maxima, and by further decreasing the wavelength, the intensity decreases. So basically, at a particular temperature, we are talking about various wavelengths of the radiation that is emitted, and we know that this is not possible. Particular electromagnetic radiation, if it has wave nature, then it carries a particular wavelength. But this experiment is suggesting something different. It is suggesting that at a particular time, these series of wavelengths is emitted by the black body. So this phenomenon actually Planck suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in a continuous manner. A belief popular at that time. Okay, so at that time it was people were starting to believe that yes, out of all of these experiments that were unable to be explained by the wave nature of the electromagnetic radiation, so people started thinking that maybe the electromagnetic radiation has a particle-like nature and non-wave like or basically dual nature is there. So Planck gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. So, and that energy, or we can say the packet of energy, the small packet of energy is represented by this simple equation given by Planck, which is E equals to h nu, where h is the proportionality constant known as the Planck's constant and has a value of 6.626 into 10 to the power of minus 34 joule seconds. So let us now talk about the photoelectric effect. So the electrons are ejected from the metal surface as soon as the beam of light strikes the surface. The number of electrons ejected is proportional to the intensity or the brightness of light. So photoelectric effect is nothing but when you shine light on the metal. So there are electrons on the metal surface. So as soon as you provide the light which is equal to the ionization energy of the metal, the electron will be knocked out from the metal surface, right? So that is what is called photoelectric effect. So you need to provide that amount of energy that is equal to the threshold energy. That is, the threshold energy is a term which is equal to the minimum energy required to knock out the electron, or we can say it as ionization energy in layman's language also. Okay, so that is photoelectric effect. For each metal, there is a characteristic minimum frequency, which is also known as the threshold frequency, below which the photoelectric effect is not observed. So this cannot be explained by classical physics. Okay, so this cannot be explained by classical physics, and because here light has to have particle-like character. Because if like packets, light can be imagined as packets of energy, and that packet of energy will have the energy which is equal to or greater than the threshold energy of the metal. That packet of energy is absorbed by the metal surface and the electron is knocked out. And if the packet of energy is less than the threshold energy, then no electron will be emitted. So this is the pictorial representation of photoelectric effect. So it was actually uh, found by Einstein in 1905. So this is the metal surface and there are electrons on the metal surface. As you provide the energy to the metal surface, and if that energy is equal to the threshold energy or greater than that, so that electron will be emitted out. So this is the kinetic energy, and obviously that energy will be the electron will be ejected out, and that electron will also have some kinetic energy. So it depends upon this equation, which is h nu, that this is the energy that you provide, h nu naught, which is the threshold energy, or in other terms it is the work function of the particular metal, and this is the kinetic energy half mv square. So this is the kinetic energy that the electron will carry when it gets ejected out. So now in this lecture we have proved that there is dual behavior of the electromagnetic radiation, that is some of phenomenon like black body radiation, photoelectric effect is understood by the particle nature, and interference and diffraction is explained by the wave nature of the radiation. Hence both particle and wave nature of electromagnetic radiation was accepted at that time, right? And still it is accepted. So let us now jump into the question answer series. So we will be dealing with question number 2.5 to 2.12 in this particular lecture of the NCERT exercise. So let us take the first question, and the first question 2.5 is that yellow light emitted from sodium lamp has a wavelength of 580 nanometers. Calculate the frequency and wave number of the yellow light. It is very easy. So we know that C is equals to nu lambda, okay, where nu is the frequency and lambda is the wavelength. So wavelength is already given, c is the speed of light that is known to us, it's a constant. Then we can easily find out the missing, that is the frequency. So from here you can find out the frequency, and also by just solving this equation. So c is equals to 3 into 10 to the power of 8 meter per second, that is equals to nu, which we need to find out, into wavelength that is already given. So it is 580 into 10 to the power of minus 9 meter. You need to write it in meter because here also it is in meter. So you have to maintain equal units. So from there, if you divide it then you will get the answer of nu equals to 5.17 into 10 to the power of 14 per second is the answer. And now you need to find out the wave number also in the question. So wave number is nothing but the reciprocal of the wavelength, and wavelength is directly given in the question, so you just have to divide it by divide it like this, 1 upon 580 nanometer inverse. So that gives the answer as 1.72 into 10 to the power of 6 per meter. I have converted nanometer into meter by simple mathematical calculation. So, question number 2.6. So, let me read out the question first. So, find energy of each of the photon, which number 1 corresponds to the light of frequency 3 into 10 to the power of 15 hertz. Okay, so you need to find out the energy, and nu is given. So you simply have this equation of energy is equals to h nu. You need to find out the energy. Nu is already given, and h is nothing but the Planck's constant and has the value of 6.626 into 10 to the power of minus 34 joule second. So after multiplying h by frequency, here comes the answer of 1.9878 into 10 to the power of minus 18 joule. And in the second part of the question 2.6, it is asked to find out the energy of each photon which has the wavelength of 0.50 angstrom. So first of all, you should know to convert the units. So angstrom, 1 angstrom is equal to 10 to the power of minus 10 meters. So wavelength is given, you need to find out the energy. In the previous question, frequency was given, you need to find out the energy. Here also we will use the same equation, but just the another form of that equation. So we already know that E is equals to h nu, and we also know that nu is equals to c upon lambda, and that is why we are substituting nu by c upon lambda, so which makes the equation of E is equals to h c upon lambda, and we put the all the values. H is the constant that you need to memorize, that is in joule second. You need to put the constant c again, that is meter per second, and you need to put the wavelength that is given provided in the question. You have to remember that you need to provide the wavelength in the unit meter, because above also it is in meter, speed of light is in meter, so here also you need to put it in meter. If you put it in angstrom, you won't get the answer correct. So here by uh, you can see per second and second is cancelled, and meter is cancelled, so you are left with joule, and the energy is the unit of energy is joule. So your answer is 3.98 into 10 to the power of minus 15 joule. So the next question is 2.7, which is calculate the wavelength, uh, frequency and wave number of a light whose period is 2 into 10 to the power of minus 10 second. Okay, so what is period? So before that, you need to solve this question by units. So period is given in second, and the energy parameters are E, lambda and nu that you need to find out, that is energy, wavelength and frequency. We know that the unit of frequency is per second. So from here you will get an idea that if you divide this period, like reciprocate this period, like 1 upon period, that will give you the answer in unit per second. So that is equal to the frequency, right? So the unit of frequency is nothing but per second. So that is why you will use this formula. Frequency is equals to 1 upon period, and period is already given. So 1 upon 2 into 10 to the power of minus 10, and the unit will be per second. 1 upon second is per second, and the answer will be 5.0 into 10 to the power of 9 per second. So once you get to know about the frequency, then you can easily put this equation of C is equals to nu lambda, and you can easily find out lambda. So lambda is equals to C upon nu. C is the constant and nu, you just find it out. So now if you divide it, then you will get the equation as the answer as 6.0 into 10 to the power of minus 2 meter. Again, you need to find out the wave number, and wave number is given by 1 upon lambda, and you just took out lambda, so you just reciprocate this value and you will get the answer in per meter, which is 16.67. I hope I'm clear with all of these. In question number 2.8, it is asked, what is the number of photons of light with a wavelength of 4000 picometer that provide 1 joule of energy? So here you are provided with the wavelength that is equals to 4000 picometer. Also you are provided with the energy which is equals to 1 joule, and you need to find out the number of photons that is equivalent to that much of energy. So we already know energy is equals to hc upon lambda. So this is equal to 1 photon. So if you divide it by n, then you can easily find out the number of photons that is there, that together forms 1 joule of energy. So here you need to here n will be E into lambda upon hc. So if you put the value of energy in joules, and then you need to convert this picometer into meter, which is 1 picometer is equals to 10 to the power of minus 12 meters, and then you have to put the value of h, you have to put the value of c in meter per second, and if you calculate, then you will get the number of photons that is equivalent to energy of 1 joule. So that is equal to 2.01 into 10 to the power of 6. Here there will be no unit. You will when you will calculate, and you can see also here that all the units will get cancelled if you have everything in SI unit. So make sure when you are solving any question, you need to put all the variables in a particular unit. For say SI unit, so you have to keep all the variables or the constants in SI unit, and then you can easily cancel out few of the units and you will get to your answer. So here the number of photons is asked, and it will be unitless because it is numbers. Question number 2.9 is asking, a photon of wavelength 4 into 10 to the power of minus 7 meter strikes on metal surface. The work function of the metal is also given. It is given as 2.13 electron volt. Now you have to calculate the energy of the photon, and also that the photon, that is the energy of the photon means that the energy you are providing to the metal. Okay, and this question will be solved from the last equation we studied in this lecture. And also you need to find out the kinetic energy of the electron that is emitted, and also you need to find out the velocity of the photoelectron emitted. So this is a lengthy question. So let's solve it. So if this question will be solved just by one equation, which is h nu is equals to h nu naught plus half mv square. Half mv square is nothing but the kinetic energy of the electron, which is also asked in this question. And also after you find out this kinetic energy, then you can put the value of mass of electron, then you can easily find out the velocity of the electron, which is also asked in the third part of the question. So the first part of the question asks you to find out the energy of the photon. So energy of photon is equals to hc upon lambda, right? So it is the very first equation that you studied. So you need to put the values of h and c, which are constants, Planck's constant and speed of light, in joule second and meter per second respectively. And also you need to put the value of lambda, which is given in meters. So here you don't need to change anything with the unit because it is already given in the SI unit. So if you calculate it, you will get the value of 4.969 into 10 to the power of minus 19 joule. But in the question, it is written that you need to find out this energy of photon in electron volt. So you need to know this conversion of unit. So 1 joule equals to 6.242 into 10 to the power of plus 18 electron volt. So here you just have, in place of joule, so you have to write this. So if you multiply the answer with this whole entity, then you will get the answer as 3.10 electron volt. Now you have to find out the kinetic energy, so that you can easily find out using the photoelectric effects equation, which is nothing but h nu is equals to h nu naught plus half mv square. So this is the kinetic energy, so write it as kinetic energy. And now kinetic energy equals to h nu minus h nu naught, right? So we know h nu naught. It is given in the question as 2.13 electron volt. And again, you have already calculated h nu as 3.10 electron volt, and both the equation are in electron volt, so you don't have to change it. So kinetic energy also you will get by subtracting these two energies, and that will also be in electron volt, and here it is equal to 0.97 electron volt. After that, in the third part of the question, it is asked to calculate the velocity of the electron. Now you have to open this kinetic energies equation, which is equals to half m v square, where m is the mass of the electron. So you all know the mass of the electron from the previous lectures. It is equals to 9.109 into 10 to the power of minus 31 kg. And when you solve this equation, then you will get to your answer. Please try and always keep all the values in SI unit. Then we will reach to your answer in meter per second. So question number 2.10. The electromagnetic radiation of wavelength is given 242 nanometers is just sufficient to ionize the sodium atom. Now calculate the ionization energy of sodium in kilojoule per mole. So this question is very simple. It has just tried to fool fool you. So what the question is asking is that it has given the wavelength of light that you are already putting to a sodium metal, and it has asked you to find out the ionization energy of the sodium, which is just sufficient. Okay, so that is the kinetic energy of the electron will be 0. So if we put that equation of h nu equals to h nu naught plus kinetic energy and put that kinetic energy to 0, then your equation will be reduced to h nu equals to h nu naught. Okay, and you are already provided with the lambda value, so you can easily change this h nu to hc upon lambda, and that h nu naught will be nothing. It is a threshold energy, or threshold energy in other terms you can call it as ionization energy of sodium atom. So when you calculate this by putting the value of hc and lambda, you will get to know the ionization energy of sodium, and that will you will get in joule. But this ionization energy is for one sodium atom, and in question you need to find out the energy in unit of uh, it will be kj. Okay, it will not be kg. So in question you have it is asked to find out the answer in kilojoule per mole. So that means first of all you need to convert this joule into kilojoule, and also this energy value is just for one sodium atom. You need to calculate it for 1 mole of sodium atom, and we know that 1 mole equals to 2.022 into 10 to the power of 23 sodium atoms. So you just have to multiply it by this particular energy. So ionization energy for 1 mole of sodium will be uh, energy for 1 atom of sodium into number of sodium atoms in 1 mole or per mole. So that will give you the answer in joule per mole, and then you need to find it in kilojoule. So 1 joule equals to 10 to the power of minus 3 kilojoule, and this way you will get to the answer. Here it will be kj per mole minus 10. So now question number 2.11. This question is a bit tricky, but it is very easy because it will be solved by the very simple equation. So it says as a 25-watt bulb emits monochromatic yellow light of wavelength is given 0.57 micrometer, and also the watt of the bulb is given as 25 watts. Okay, you need to calculate the rate of emission of quanta per second. So you need to find out number of photons or quanta, they are same. So you need to find out the number of photons per second that is emitted. So we have that equation which is E is equals to NHC upon lambda, where N is nothing but the number of photons. Okay, and here watt of bulb is given. So watt of bulb is nothing but joule per second. Okay, so energy emitted per second. So if you have here watt, here you will have N, then both are in per second. So if you have watt here instead of energy, then you will get number of photons uh, uh, per second instead of number of photons. Okay, so you just put 25 in energy, and n it will be the number of photons emitted per second, and you need to put the value of hc upon lambda. Lambda is also given in micrometer, that you need to convert it into meter. So 1 meter equals to 10 to the power of minus 6 micrometer. So sorry, 1 micrometer equals to 10 to the power of minus 6 meter. So that is why that is how you will calculate this, and you will get the number of photons emitted per second. So the last question that will be discussed in this particular lecture is question number 2.12. So here the question says electrons are emitted with zero velocity. Okay, that means the kinetic energy of the electron that is emitted after
striking on the metal is 0. So the first line is telling that the kinetic energy is 0, which is when exposed to radiation of wavelength. So wavelength of light that you are putting to that metal is also given um, in angstrom. So calculate the threshold frequency, that is the h nu, and the wave function of the metal. So you need to find out two parameters. First is the threshold frequency and another is the wave function. So you just have to put this equation of h nu equals to h nu naught plus kinetic energy, and in the first line itself it has mentioned that the kinetic energy is 0. So you just need to eliminate that term. So now you have the equation h nu equals to h nu naught, and h nu naught is nothing. The whole these two terms is equal to the work function. So which is asked in the second part of the question. In the first part of the question, you need to get the threshold frequency. So when you write the equation like this, h nu equals to h nu naught, then h and h will be cancelled, and h nu naught will be equal to nu. And nu in the question is provided by the wavelength. So mu is equals to c upon lambda. We already know. You need to convert angstrom into meters, and 1 angstrom equals to 10 to the power of minus 10 meters. And then if you divide c upon lambda, then you will get the threshold frequency, which is equal to 4.41 into 10 to the power of 14 per second. After that, you need to calculate the work function, which is nothing but h nu. So you need to multiply this nu naught that you found just in the question into the Planck's constant, which is 6.626 into 10 to the power of minus 34 joule second. And this second and this second inverse will be cancelled, and you will get the answer of work function in joule, which is equal to 2.92 into 10 to the power of minus 19 joule. Thank you.